Hi, good evening, people. So the time now is what? 10 past 11 on the eve of Deepavali. Happy holidays, people. So anyway, as promised, I'll be trying to record the remaining part of Turbomachinery chapter so that we can get all the lectures over and done with. And if that can be done through this video recording, that means for next Wednesday, we will be able to go through the tutorial for turbomachineries and as well as a review session, whereby I'll go through all 4 chapters briefly, just to have a recap of sorts. Okay, and hopefully by next Wednesday we will be able to finish all lectures plus tutorials. Okay, so anyway, I hope you guys can see the screen. I believe I've shared the screen already. Just let me double check here. Okay, so this is where we last stopped. Okay, the last time we stopped, I believe we were talking about dimensionless pump performance, and over here will be a quick example to illustrate how we will be able to make use of dimensionless pump performance parameters to help us to solve questions. Okay, so let's quickly run through the example. All right, we have got a centrifugal pump, okay, that has got a 20 cm diameter impeller, and this pump is known to belong to the same series as another centrifugal pump with a 30 cm diameter impeller. So they belong to the same family. So basically the designs are the same, it's just a matter of how big they are. So the figures below, show the pump performance characteristics of the latter pump at 1000 RPM. So, well, I suppose it's figures on the side because I don't have space below. So now based on these charts, estimate the discharge, the pump head, and the shaft horsepower of the smaller pump running at peak efficiency and 1200 RPM. So now, as I've mentioned, these 2 pumps come from the same family, so they are what we call geometrically similar. And that also means that we can assume, all right, that their peak efficiency is the same. So if you think about it, that means that, all right, we will be able to make use of this chart to locate the peak efficiency point, all right, such that we'll be able to get the intersects with the other graph to get us the various coefficients, such as CQ, all right, that's the capacity coefficient, CH, that's the pressure head coefficient, and CP, the power coefficient. So if you think about it, I'm quite sure, all right, this, you guys can see, right? This curve is the efficiency curve. So this curve is pretty much the same. So we just make use of this curve to get the various coefficients. So we go and try to estimate the point, the best efficiency point, and basically drop down line. And I'm quite sure you guys can tell that once you drop down line, you guys will be able to get various intersects. They'll give you approximate values of CH over here, CP over here, and of course CQ on the x-axis. So we have got 2 y-axis here. First y-axis on the left will give us the value of CH. The second y-axis on the left, on the right, will give us CP, and the x-axis will give us, all right, the CQ. So from these various intersection points, you guys will be able to get these coefficient values. Okay. Now, the approaches to solving for the discharge, which will be Q, the pump H, which will be H, and the shaft horsepower will be P. At the end of the day, the approaches will be quite similar, except that the definitions of the coefficients may be quite different. So I'm just using CQ, all right, as an example for us to find out what's the absolute discharge based on the values gotten. So we know CQ's value is 0.0625. So, all right, that sort things out for us on the left-hand side. But we are interested in finding out what's Q. So we move the denominator and dq to the left-hand side, shuffle the terms around. We're going to get Q equals to CQ and dq. We know our CQ value is 0.0625. Our N, I believe I put it as 1200. It should be 1200 divided by 60 because N is in revolutions per second. So I think I forgot to divide by 60, but you guys can correct it to be 1200 divided by 60. Sorry about that. D, in this case, we know what's the diameter. Well, we're talking about a smaller pump, so the diameter will be 0.2 meters. And then, of course, you have to take the Q. Okay, I'll leave it to you guys to punch out the numbers. All right, punch all these numbers in the calculators and get the answer. All right, and that will be your discharge. Simple as that. So the most important thing about this example is to be able to read this graph, all right, get the values, approximate values of the various coefficients and the mix of coefficients to scale things up and down, or in this case, try to find out the absolute values for the discharge, pump head, and horsepower. Okay, so I'll leave. All right, I'll leave it to you guys. All right, to basically continue the pretty much the same procedure to find out what's H and find out what's P using this. Okay, I think this will be a good exercise for you guys. Just based on this, I'm quite sure you guys will know what to do. Okay, now let's move on to something else. Okay, let's move away from dimensionless pump performance and move on to specific speed of pumps. So specific pump speed allows engineers, okay, this particular parameters allows engineers to easily select the most suitable pump type for their end applications. So let's say, right, you do not have a particular preference, right, whether to use a radial type pump or axial type pump or mixed type pump. You just want to have a pump that can get the job done. And so what happened is, in that case, we will have the ability to make use of this particular parameter known as specific speed to help us choose the pump. And this can be done, all right, by emulating the diameter parameter, okay, by using CQ and CH. So NS, okay, that will be a specific speed, okay. After sorting things, basically you take CQ, all right, divide by CH after you raise them to the appropriate powers. Okay, at the end of the day, once you simplify this, you're going to get this. So NS is defined as N square root of flow rate Q divided by GH raised to the power 3/4. So as you can see over here, all right, there's no more diameter term. Okay, so what happens is if you plug in all these, let's say you plug in values of these variables, all right, based on the requirements, you're going to work out NS value. And what happens is, okay, once you know what's an NS value based on this definition, you can basically make use of charts like this. All right, we should be looking at the second horizontal axis here, which is the specific speed. So whatever number they got up from this calculation, all right, and basically go down this list, okay. And depending on the value of this, of the specific speed they just calculated, okay, they will tell you, all right, what sort of pumps you should be using. All right, for rather low values of specific speed, chances are, all right, you will need to use a radial flow type pump, okay? For let's say rather high specific speed, right, probably you will have to use an actual flow type pump. Somewhere in between, all right, it's probably all right better that it goes for a mixed flow type pump, okay, whereby the pump has got characteristics that belongs to radial flow types as well as axial flow types, okay? Now, so just to summarize again, centrifugal pumps, right? They will be typically used when the specific speed are rather low, let's say less than 1.5, while axial flow pumps are typically used when the specific speed are greater than 3, thereabouts. Now, for specific speeds of values that lies between 1.5 and 3, we tend to go for mixed type pumps as well. Okay, so as I've mentioned, mixed type pumps are sort of like jack of all trades, right? That they have common characteristics with both radial flow types as well as axial flow type pumps. Okay, now there's no hard and fast rule, you know, that you can't use, let's say, a centrifugal pump when the specific speed is, let's say, 2. All right, it's just that you may not be using it at the most efficient. Okay, all right. So this is just a general guide. It's not hard and fast rule. Okay. And the good thing is all pump similarity rules and coefficients that we talked about earlier, they're all applicable to all pump types. Doesn't matter if it's a centrifugal pump, axial pump, or mixed type pumps. Okay. And over here shows some of the differences between the characteristics of a centrifugal pump and axial flow pump. So I'll let you guys take a look at this graph and basically deduce or figure out what's the differences. Okay. All right. Clearly, there's some differences here. Okay. So the solid line here represents the characteristics of the centrifugal pump, right? Whereas the dashed line will be those associated with axial flow pump. So you guys can take a look to figure out some of the differences between axial pumps and centrifugal pumps. Okay. Let's move on. Now, since we're going to move into axial flow pumps, it might be a good idea for us to have a good idea. Generally speaking, all right, axial flow pumps, right, or axial pumps, okay, they tend to have static stator blades and rotating rotor blades. Okay, the word rotor means that it's rotating, right? All right, while the word stator means that they're stationary. Now, it is possible, all right, that the stator blades are before or after the rotor blades. Okay, there are no hard and fast rules. Depends on what your application is and so on and so forth. But at the end of the day, the primary so-called role of stator blades is to basically reduces any flow swirl. All right. Okay. Once the fluid has passed through the axial pump. Okay. Now, as the name implies, okay, axial flow pumps, all right, basically outputs fluids axially. All right. They don't pump out the fluid, okay, radially like centrifugal pumps. Okay. So basically essentially this, I suppose this picture paints the picture rather well. So once you start to spin the rotor blades here, right, the water gets sucked in here, and after passing through the rotor blades and the stator blades, it continues in the same direction. It doesn't like go off in the radial direction. Okay. So yeah, so over here, clearly we have a situation whereby we have the rotor blades right upstream of the stator blades. But of course, it is possible to have a situation whereby we have the stator blades before the rotor blades. Both are equally fine, and the objectives of the are pretty similar as well. Basically, is to reduce flow swirl, which will in turn lower flow losses and perhaps leads to lower noise level and hopefully higher efficiency. Okay. Now, similar to centrifugal pumps, axial flow pumps can be analyzed using velocity triangles. So let's say this is a row of stator blades, this is a row of rotor blades, and flow is moving from top to bottom. Okay, even though this diagram shows the velocity triangle being constructed at the trailing edge of the stator blades, okay, this velocity triangle can be sketched at the leading edge of the rotor blades as well. All right, and of course, we will have another velocity triangle at the trailing edge of the rotor blades. Okay, just like what we have done for centrifugal pumps. And the formulas are relatively similar, subjected to a few changes. Okay, now there's a few assumptions. There are a few assumptions when it comes down to looking at the actual flow pumps analytically in terms of the velocity triangles, and they're largely similar to what we have assumed for centrifugal pumps. Right? For example, well, I suppose this is not for centrifugal pump, but more for axial pump. So for axial pump, the assumption is we're looking at one-dimensional flow only, okay, and that the flow leaves each stator blade. That means this stator blade. That means they're stationary, at a relative velocity exactly parallel to the blade exit angle, and transits into the rotor entry blade. That means it transits into the rotary entry blades parallel to its leading edge. So basically, the flow must flow onto the rotor blades in a nice and smooth manner. Okay. So from the status perspective, that means from the status perspective, V1 should be parallel to the status blade trailing edge, such that, all right, the flow is able to exit smoothly from the stator blade. On the other hand, W1, okay, which is this triangle here, this W1 should basically be parallel to the rotor leading edge, as I mentioned earlier on. So this is W1. So if you translate this triangle over here, so this would be W1. You want the W1 to basically flow around the aerofoil shape, like, all right, pump blades, okay, rotor blades, okay. Now, from the rotor's perspective, okay, you want V2 to be parallel to the next stator's leading edge, all right, because all right, if there's a next stator, right, there's no guarantee there's going to be another stage of stator. But let's say for multi-stage compressors, you're going to have, let's say, a row of stator, rotor, stator, rotor. And you want to make sure that whatever flow that leaves the rotor is going to enter the next row of stators nicely. All right, and so on and so forth. Okay. And you want W2, which is the flow that's leaving the rotor trailing edge, to be parallel, right, to the trailing edge, such that there's no flow separation. The flow is able to basically flow away from the rotor blade smoothly. Okay, so all these assumptions are by and large similar to what we're seeing for the centrifugal pump for very idealized flow scenarios. Now, the equations associated with axial flow pumps are relatively similar to those that we covered for centrifugal pumps earlier on. So some of the equations are basically can be used here, but subjected to certain changes, because ultimately we're still looking at a slightly different type of pump. Okay, all right. So let's take a look at some of the differences. Okay, now there are no radial flows in the axial flow pumps, clearly, because they wouldn't be called axial flow pumps, right? So in that case, the inlet and the exit rotor speeds are actually similar. All right, so that means U1, all right, is actually equals to U2. Okay, And if you think about it, since we assume there's a 1D flow and 1D continuity requirement meant that Vn1, the normal component of V at the inlet, must be equals to Vn2, the normal component of the velocity at the blade exit. Okay, since they are similar, we can just write them as a common Vn. And this Vn is nothing but the flow rate that's going into the actual pump, right, divided by the cross section of the actual pump. Okay, and this is a constant for that particular scenario. And from the velocity triangles that we see earlier on, it can be deduced, all right, that the blade tangential or the tip speed U, all right, can be basically approximated as the average radius of the rotor, okay, multiplied by the angular velocity omega. Okay, and U, all right, if you take a closer look at the velocity triangles, okay, can be said to be equals to, can be worked out to be equals to Vn1 into cotangent alpha 1 plus cotangent beta 1. So all these are the parameters associated at the rotor inlet. Okay, but however, we can also relate U to that of the rotor exit, because ultimately, if you think about it, U1 actually equals to U2. All right, so this Vn1, so U can also be said to be Vn2 into cotangent alpha 2 plus cotangent beta 2, just based on the velocity triangles. Okay, and there are other things that we can get out from the velocity triangles. Okay, that's a good thing about velocity triangles. There's no need for you to memorize these equations, actually. All right. So sometimes you can just look at the velocity triangles and you can deduce these. But anyway, I'll just list them out here. Okay, from the velocity triangles, we can also work out that Vt1, the tangential velocity component of V at the inlet, equals to Vn1, the normal component, multiplied by cotangent alpha 1, and that Vt2 is equals to U minus Vn2 cotangent beta 2. Quite similar to what we've encountered earlier on, isn't it? Subject to some change. How about pressure hit? How about power? And so on and so forth. Okay, if you recall, power is related to this term, GH. And in this case, all right, GH is defined, or it can be worked out from the velocity triangles as equals to UVN into cotangent alpha 2 minus cotangent alpha 1. Or it can be expressed in this form, all right, once you manipulate some of the expressions. Okay, so by and large, the expressions are similar with the centrifugal pumps subjected to certain unique tweaks and changes, because ultimately the flow is still flowing actually after it passed through the rotor. Okay, so I encourage you guys to check out the textbooks, because textbooks will give you a lot more details. Now, some of you guys may not like to read textbook because it takes such a long time, but my suggestion is, instead of worrying yourself sick when you have no idea what these formula are and how they are being derived and things like that, what do they mean, rather than worry for like 2 days sick, why not just borrow a textbook, read it for an hour or two, and basically feel a lot better, all right, and achieve much better understanding. Okay, all right, so this is my recommendation. Okay. Now, we've been talking about pumps, centrifugal pumps, actual pumps, whereby work is being done upon the fluid. Now, how about the other scenario whereby we are extracting energy from the fluids? In that case, we'll not be talking about pumps, but we're talking about turbines instead. Okay, so when it comes down to extracting energy from moving fluids, let's say in this case water, it's probably a lot easier to visualize. There are two important turbine types that are commonly used. Okay, there are other turbine types, but these two will be more important. The first one will be known as the impulse turbine, okay, which are meant for high pressure head but low flow rate scenarios. Okay, but reaction turbines will be used when they're talking about a scenario that is associated with low pressure head but high flow rate. Okay, and what happens is geometries of turbines, right? In this case, they're designed such that water, all right, will exert a torque on the rotor in this direction of these rotations, and these rotations will basically rotate the rotor, and this rotor will basically drive dynamos or generators to produce electricity. So by and large, that's the function of turbines. Okay, now let's take a look at impulse turbines. An impulse turbine is one of the simplest form of turbines. Well, one might say that this is simple as hell. Pardon my use of the word. It's like a water mill, and in fact, you will be right. It's something like a water mill. So with respect to the figure over here, so imagine we have a relatively large wheel, and at the circumference of these wheels, we're going to have all these various buckets, and we have a jet of water all right, that's set to collide or impinge upon these buckets, right? Such that the buckets, right, will basically go round and round and round. And right, at the end of the day, there's going to be a shaft, not shown here, right, that's rotating as well to drive a dynamo, a generator, and things like that. Okay, all right, but there are certain, I mean, even though it sounds conceptually simple, but actually, all right, they're highly refined devices, all right, which we have used for, basically we'll be using them for many things, just to produce energy, to drive machineries and so on and so forth. So their designs are very well known, very well established, and it's quite easy to analyze them. Okay, so such a device or such a setup is what we call a Pelton wheel. And it represents one of the simplest way to extract momentum and hence energy from the impulse of the moving water. Well, it may not always be moving water, it can be some other fluid, but water is one of the most common fluid, right, used to drive these devices. Okay. Now let's start to analyze the situation, right, this particular scenario. Okay. Now, if you take a closer look at the bucket, now over here, it looks like a very simple bucket, but there are ways for us to tweak the design of the bucket's geometry such that we are able to extract the maximum energy. Okay. So if you take a cross section of the bucket, it's going to look something like this. All right. So what happened is, okay, the water is going to hit the bucket, and because of this relatively interesting design of the bucket, it's going to split the jet stream into half, right, with the water sort of like making a U-turn. Okay. But before we go there, let's take a look first. All right, let's start up with the more fundamental stuff. So let's say this is a schematic. So the pink color region basically represents the water, and this gray color region represents the cross-section of the bucket. So we're literally looking at the cross-section of the scenario. Okay. So what happened is, let Vj be the velocity of the water jet that's hitting the bucket, and let U be the velocity at which the bucket is traveling. And of course, in this case, it will be the tangential velocity of the Pelton wheel, if you think about it. So what happened is, okay, based on these two velocities, we know that, right, the effective jet velocity, okay, when the water hits the bucket, surely must be the difference between the absolute jet velocity and the tangential velocity of the bucket, which is U. So basically, the effective velocity, right, would be Vj minus U. Okay, and what happened is, because of the design of this bucket, the water will actually leave the bucket at this velocity at an angle that corresponds to the bucket's exit design angle beta. So this angle over here, right, this angle, that means the angle made between the axis of the jet's direction and the curvy bit here. So you can look at it as the direction of the water here. So this angle is angle beta. Okay, all right, so that's the scenario. Okay, now if you base on, okay, so basically we can actually construct the velocity triangle, okay, for the scenario here. Now, based on this velocity triangle, all right, we can actually find out that the force per unit mass on a single bucket, right, will be the product of the effective jet velocity, which is Vj minus U, multiplied by 1 minus cosine beta, just based on this velocity triangle. Okay, now this is the force per unit mass. Okay, so the power produced by a single bucket, right, is nothing but this term here, this product here, okay, multiplied by rho Q U, density, flow rate, and the bucket velocity. And that was going to give us the power produced by a single bucket. Okay, now just by looking at this equation, one might go say, if I want to maximize P, all right, it seems to be the case that I should make use of an exit angle beta of 180 degrees. Okay, all right, but that is practically impossible because that means that the water, all right, after hitting the bucket, is going to come back at the water discharge point. And chances are that's going to disrupt the water stream in the first place. Okay, that's not practical at all. All right, okay, in trying to achieve an optimum power, you may end up disrupting the original jet stream that's actually hitting the bucket. So in practice, a compromise will have to be struck, and through trial and error, a beta angle of 165 degrees will work right just as well, because this will still produce power, which is relatively high. In fact, it's only 2% less okay, then that produces at beta equals 180 degrees, but avoid all the various pitfalls, right? Okay, of you actually using beta equals 180 degrees design. Okay, all right. So in some ways, it's a compromise. Okay. Now we can actually find out the maximum power. Actually, we can come up with derivations and expressions. Okay, mathematically find out. All right, the operating point at which we're going to extract maximum power from the bucket or from the entire pattern width for that matter. Okay, simply what we can do is to take this expression over here and differentiate it with respect to u. All right, set it to 0 because that's how you find maximum points and minimum points. And eventually, if you sort it out, you realize that, hang on, to get maximum power, all I need to do is to make sure that the tangential velocity of the Pelton wheel, all right, is exactly at half of the absolute jet velocity, Vj. So basically, optimum u, represented by u star here, is equals to Vj divided by 2. So mathematically speaking, all right, this is what the P actually will give us if we calculate it as a function of tangential velocity of the Pelton wheel. And you can see over here, exactly at the midpoint here, where tangential velocity is 0.5, that of the absolute jet velocity, we're going to get peak power. Okay, and it's not too far off from the truth. So this red line, this solid line represents the mathematical, what we're going to get if we follow the theoretical mathematics. And the square symbols here basically shows what's going to happen in real life. So yeah, I mean, the peak value here actually occurs at maybe closer to 0.4 something. All right, that of the jet absolute jet velocity, but it's not too far off from the 0.5 absolute jet velocity estimate. All right, if we base everything purely on that. Okay, so it still gives quite a reasonably close estimate for the optimum operating point. Okay, now to illustrate what we just gone through early on, perhaps just a quick example. All right, now with reference to the figure here, okay, we have a Pelton wheel, which is this. It looks like a bloody furball. Okay, anyway, or rubber duck, yeah. So we have got a Pelton wheel here. I'm sorry about that. And it's driven by water coming off from a reservoir. So this is the reservoir issued from a pipe. Okay, so the water from the reservoir will flow through this pipe and come out from a nozzle. And it's going to come out as a jet, and the jet hits the bucket here, and this Pelton wheel can be driven round and round. So determine the nozzle diameter D1. Okay, so what happened is this D1 is actually quite a bit smaller than the pipe diameter. Because if you think about it, if you reduce the diameter, it's going to accelerate the jet velocity, and you know that may accelerate the value of Vj to 1 that's closer to the optimum point, isn't it? So determine the nozzle diameter D1 that will give the maximum power output, okay, based on the parameters given here. Additionally, determine the maximum power output, okay, and the angular velocity of the Pelton wheel at this condition. What condition? The maximum power output condition. Okay, now before we solve anything, let's take a closer look. We have got a Pelton wheel here. Okay, we're told that the diameter of the Pelton wheel here is 0.91 meters. Okay, the angle beta is 150 degrees. That's fine. That's the reservoir, and the reservoir has got a elevation pressure here of 61 meters as compared to 0.1. So let's say this is 0.0, this is 0.1. Right, at 0.1, Z1 is equal to 0. At 0.0 or 0.0, Z0 equals to 61 meters. That's quite a bit of elevation pressure here, isn't it? The length of the pipe is 305 meters. We know the friction coefficient is 0.02. That's fine. The diameter of the pipe is 20 cm. So if you think about it, this will allows us to find out what's the friction, friction loss, isn't it, of the pipe. Okay, so now armed with all this knowledge, before that, over here we let the nozzle diameter be D1. Okay. Now, so with all these things, sort of like digested in our brain, let's try to see whether we can solve this thing. Now, let V be the velocity within the pipe, not coming out from the nozzle, but within this long straight pipe, the 20 cm pipe. Okay, so let V be the velocity within this pipe before the water exhausts out from it, and let V1 be the jet exhaust velocity. So this will be V1. Okay, and surely V1 will not be the same as V. Okay, now mass continuity will basically tells us that, look, all right, mass must be conserved, and since we're talking about incompressible fluids, then its volume must be conserved. So basically the product of velocity within the pipe multiplied by the area of the pipe surely must be equals to the velocity at the exit here of the nozzle, okay, multiplied by the cross-sectional area of the nozzle. Right, so basically VA equals to V1 A1. Shuffle the terms around, we're going to get V, all right, equals to V1 A1 divided by A. But hang on, areas are functions of the diameters, of the respective diameters. And that means we can re-express this term as D1 divided by D squared times V1. Okay, so now that we have that, we just leave it there first. Okay, now since we have water that's moving, that's sort of like being discharged from a large reservoir to a nozzle with elevation pressure heat difference, that sort of like give us a very, very clear clue that we can make use of the Bernoulli's equation as an energy balance. Okay, equation that can be applied between these 2 points. A point on the surface of the reservoir and a point at the nozzle exit. Point 0 and point 1. I'm not going to go through repeat some of the stuff that we're going during unsteady flows, but suffice to say, start off with the full Bernoulli's energy balance equation and basically simplify the terms, cancel the terms until at the end of the day, this is what you're going to get. You're going to get Z naught, which is basically the elevation pressure heat difference, equals to V1 squared divided by 2G plus HL. In this case, HL is nothing but, all right, basically friction loss along the pipe flow, which I'm quite sure you guys know this already, is defined as FL divided by D, V squared divided by 2G, all right, where V is the velocity within the pipe. Okay. Now, if you combine, all right, these equations, the equations that I've seen in the earlier slide, this is what you're going to get. Okay, so you combine them such that you'll be left with an expression that relates between V1 and D1, knowing that D1 is what we want to find out at the end of the day. Okay, all right. Now, since we're interested in the maximum power output condition, all right, let's recall the formula for a Pelton wheel, all right, in terms of its power. So we know that P for a that's attracted by the Pelton wheel is defined as rho QU into Vj minus U into 1 minus cosine beta. Okay, all right. So what happened is we can actually substitute all the things we have gotten up to this point, substitute back and basically substitute into this power equation, such that at the end of the day, this is what we're going to get. So you guys can work out the details, all right, but for the sake of brevity for this online lectures, I'll just go straight to here. Okay, so you guys can do the simplification such that we're going to get expressions for P that's in terms of U, D1, and U here again, and D1 and D1. So basically in terms of, well, so basically the power equation, all right, it's going to be expressed in terms of U and D1. Okay, now thankfully we're asked for, we have to ask for the operating, we're asked for the estimation of D1 at the maximum power output. And that is a very, very convenient thing because we know that maximum power only occurs, or in theory, when U is actually equals to V1 divided by 2. If that's the case, and if you think about it, surely we can relate V1 to D1. Okay, that means I can basically run an expression for U in terms of D1. And after that, substitute back into the power equation. When I do some further simplification, I'm going to get this rather elegant expression, certainly more elegant than this. Okay, but that's because I relate everything to D1 now. And I'm going to get P equals to 15 times 10 to the power 6, D1 squared divided by 1 plus 18,750, D1 raised to the power 4, and the whole thing raised to the power 3 over 2. Okay, so now, if you take a closer look, you would have realized that, hang on, now I've got a power expression that's only in terms of D1. And since we are interested in finding out the maximum power condition, we want to find out the diameter, all right, of the nozzle. For us to do that, that means that we can simply differentiate this power P term with respect to D1 and set it equals to 0, isn't it? All right, so as to allow us to find out the maximum power point. Okay, once you set it to 0, right, once you differentiate it, set it to 0, you will have an expression or equation, okay, that has only one unknown, and that's going to be D1. So shuffle the terms around, punch the numbers into the calculators, do whatever substitutions that you need to do. Eventually, you will work out that D1. all right, has got to be 0.07 meters, so that's about 7 cm. Okay, so it's only when the diameter here is 7 cm, all right, were you able to get maximum power output for this particular scenario. Okay, all right, so this is how you typically solve a Pelton wheel problem. Okay, relatively straightforward because the equations are relatively straightforward and quite simple to remember. I'm quite sure you know this criteria. Okay, it's quite easy to remember. Okay, all right. Now that we found out what's the diameter of the nozzle, all right, we can proceed to find out what's the power, okay, at the maximum output power output point. Okay, since you know what's D1, surely you can substitute this D1 into here, and then you can estimate, all right, your power. Okay, that's produced by the Pelton wheel, and it's about 42 kilowatts. And how about the rotor speed? Well, if you want to find out rotor speed, in that case, well, hopefully you guys will remember the tangential velocity formula, which states that tangential velocity U is nothing but the product of R and omega. Since we're interested in finding out what's omega, all right, shuffle the terms around, and we're going to get omega equals to U over R. We certainly know what's R because it's given in the figure. But how about U? Hang on. You know that you're operating at the maximum power output point. That means surely U must be equals to V1 over 2. If you know what's D1, you know you can work out what's V1. If you can work out what's V1, surely you can work out what's U. Once you work out what's U, you can substitute the value into U here and work out omega. And then we give you about 302, all right, revolutions per minute, or RPM. Okay, so that's all to it. Relatively straightforward. Okay. Now, so we've talked about impulse turbines, and now let's move on to reaction turbines. Now, for reaction turbines, I don't think I want to go into the mathematics because, all right, they're usually quite complicated, and I think the scope of this module, all right, probably based on the scope, it's probably not wise of me to go to too much depth, right, when it comes out to the mathematics and so on and so forth. So I think I'll go through the reaction turbines on a qualitative basis. Okay. So now reaction turbines are more suitable for high flow rates and lower pressure hit scenarios. And just like pumps, you know, okay, we have got radial flow type reaction turbines, we have mixed flow types, we have axial flow types. Now, typically for the radial flow types and for the radial and mixed flow types reaction turbines, okay, sometimes they're called Francis turbine. Okay, so they look something like this. As you can see, the water actually sort of like enter the turbine radially before, all right, undergoing a change in direction in the actual direction. Actually, for the axial flow, the flow basically the water or any fluid actually enters the turbines more or less in the axial manner throughout. All right, as you can see over here, there's not much turning of the flow, unlike the radial flow type. Now, the axial flow types. Turbines, reaction turbines are typically known as Kaplan turbines as well. So over here, you guys can take a closer look at the schematics to have a good understanding of how some of these turbines, reaction turbines actually looks like. Okay. So just like centrifugal pumps, okay, turbines also, all right, has got so-called pump curves or turbine curves. Okay, so similar to the pump curves that we've seen earlier on, all right, we do have coefficients that relates to the hydraulic coefficient, all right, the capacity coefficient, and the power coefficient, and so on and so forth. Okay, all right. Of course, they look quite different, isn't it, from that of from those of the centrifugal pumps we covered before? Because if you think about it, well, they have got to be quite different, isn't it? One is a pump, one is a turbine. All right, one does work on fluids, one extracts energy from fluid. Okay, and just like pumps, well, there's actually a specific speed for reaction turbines as well. And you guys can take a good look at this. Okay, so what happened is just like what we've seen for pumps earlier on, for different specific speed range, right, it's probably a good idea to use, let's say, a certain type of turbine. It's not a hard and fast rule, but it's more like a recommendation. So as you can see over here, the specific range, let's say 1 to 10, the impulse turbine, it's probably recommended. But if a specific speed range, right, basically goes up quite high, chances are we should use the Francis type. turbine, and so on and so forth. Over here shows a graph as well. So there are many, many different types of tables and graphs that you can refer to in terms of the specific speed for both pumps and turbines. Okay, you guys just have to pick something that you trust. Okay, all right. And I believe this is the slide that everyone is waiting for. So that's all to it. To my part of MA4002, all right, fluid dynamics. Okay, and I thought, since we're talking about pumps, I'll just put pumpkins. I know it's lame, but hey, cut me some slack. Yeah? It's 11:50, close to midnight, so I need some laughter in my life. Okay, so anyway, I hope you enjoy my part, all right, which, of MA4002, all right, fluid dynamics, and I hope you guys have learned plenty about the 4 chapters that I've covered together with you guys. All right, equations of motion, potential flow, unsteady flows, and of course this particular chapter, the present chapter, turbomachineries. Okay, and I hope the way I taught you and the knowledge that you guys get up from this part of teaching by me will sort of like get you guys to get interested or perhaps even excited over certain aspects of fluid dynamics. If that's the case, if that happens, I believe my job is done. If not, I'll try harder. Okay, talk to me. I'll try my best to get you guys excited about fluid dynamics. Okay, so yeah, I think that will conclude my video. So next week we'll have our tutorial on Wednesday in week 13 in the first hour, and in the second hour we'll have a brief overview, a review for the 4 chapters. And with that, adios muchacho. All right, good night, and I'll catch you guys next week. Thank you very much.